Okay, this is the first of a three-part lecture on color, theory and practice. And in this first one, we're going to be focusing on the science of color, the physics, the psychology, the perception of the actual color phenomena that we see. It's not something a lot of art students get. They're usually dealing more with the mixing and the interaction of color, and we will definitely come to that. But it does provide a level of understanding so that when you're working with color, you can answer a lot of the questions you might have about why something doesn't work or why something does work. Now, you don't have to be an expert on the science of color to use color. You can be a great artist and not understand the first thing about the science or perception of color. In the same way that you could be a really good driver and not really understand how an engine works. But if you are going to learn about color, it's important to learn about it correctly. And there is a lot of misunderstanding surrounding the area of color, which we'll pick up on and talk to in a bit. So we're going to start with a simple question: what is color? When you think of color, what is it? Where, or more importantly, where is it? And we look out into the world, and it seems to make sense that it's in objects. So certain materials, vehicles, buildings seem to possess color. Grass appears green, strawberries are red, the sky looks blue, and so it kind of makes sense to think of color as being a property of objects. But as we'll see when we look into the science of it, it's a very, very different scenario altogether. And there is one interesting aspect about color and the history of color, and that is that there's a conflict between the theory and the reality. What I mean by that is there's been a lot of stuff written about color that people have taken on board and digested and accepted, and that really runs counter to the facts. So these are some of the things we're going to be talking about. So what we want to do is we want to focus on what we can see. So you look at this image. How many colors can you see? You might count 5, you might count 6, 7, 8, 3, I don't know. But what happens is, very often, if I present this to a class, they will say 7. And I ask why. And everybody says it's what they learned in school. So this is what I'm talking about. What we learn and what is the reality don't always coincide. Do you actually see 7 colors in here? Do you see less than 7? What about this slide here? Do you see any unusual colors? You should see a repetition of colors down here, where we have these 2 violets and purples and interspersed almost with an olive and a blue-green happening. These are called supernumerary colors. And the point I'm trying to make is that color changes, and that if we stick rigidly to an idea we have about color, as an artist, we're going to run into trouble pretty quickly. So if we go back in history, the first person to put color really on a scientific footing was Isaac Newton. And he's famous for a great many things if you've studied science. But one of the things that you might be aware of in terms of Newton was his prism experiments, where he shined light through a prism, and what came through the other side was a spectrum or a rainbow. Now, he wasn't the first to do this. People had been doing this for millennia, using glass and containers of water. This was not a new phenomenon, but he was the first to really try to explain it and understand what's happening. And in his explanation, he stumbled upon something very interesting that people were not aware of. And so here's a schematic diagram of what he actually did. Darkened a room, cut a hole in the window shade, let a beam of light through, let it pass through a prism, and on the other side of the room, projected onto the wall, was a rainbow of colors, which he called a spectrum. What he hypothesized from this is that the colors are actually contained in the light. Now, this was revolutionary because people prior to Newton had felt that, for the most part, colors were properties of objects, things, materials. And Newton said, no, the color that we see in the world comes from the light that illuminates the world. And he tested that by recombining the colors. There's another diagram. Here's light coming in, goes through a prism, separates, goes through a second prism which is inverted, and it creates a reverse for the process, and all of a sudden he had white light coming out the other end. So he recombined the colors. So what Newton was getting to, was that if we crack light open, if we spread it out, if we open it up through a process called refraction, that is passing it through a material that's denser than air, then what it does is it slows down different wavelengths of light. And that those wavelengths, when they spread out, create the appearance of colors. Now, one of the things that came out of all of this was Newton's famous 7 colors: red, orange, yellow, green, blue, indigo, and violet. Different cultures have acronyms for this. Roy G. Biv is one that school children are taught very often. But what's interesting about this is that, well, Newton didn't have very good eyesight, or rather discrimination of colors. He had an assistant work with him. If you read the book Optics, his assistant is telling him how many colors are there and where their boundaries are and stuff like that. Probably part of that reason is he used to experiment by sticking needles in his eye and wiggling them around so he could see kind of colors that don't exist in the world, and then he'd be blind for 3 or 4 days until he recovered his eyesight. They don't make scientists like that anymore. But anyway, he was also a very religious man. He wrote more on religion than he did on science. And he was disturbed by the fact that there might have only been 6 colors. There were 6 main colors that he perceived, or his assistant perceived. And he felt that, God had created the earth in 7 days. There were 7 visible planets. And most importantly, the musical scale had 7 notes. So he felt like God could not create a world that had a 6 in there. So he decided he'd throw in another color, and he invented this idea of indigo. Now, indigo is a real color, but it's not something you see in the rainbow necessarily. So he stuck indigo in there, and in his notes, he's quite explicit about the fact that he did this to harmonize everything with the musical scale and God's design. So there's the first step, right? We're taught 7 colors, and one of them is just completely fabricated by Newton to fit his pre-existing ideas about how the world should be. So the breakthrough with Newton was that color is contained in light, right, which is very, very important. And we can see that if we take different lights, and these are the primary colors of light, which are different than the primary colors for painters. This is RGB. You see that on your computer screen, your television. There's only 3 colors. There's a red, there's a green, and a blue. And these, for lack of a better explanation, represent 1/3 of white light. And if you take this third and this third and this third, and you put them all together, you get white. If you just take 2 of them and put them together, you get another color, but notice that that color is closer to white. It's brighter and lighter. So what's interesting with colored lights is if you mix green and red, you get yellow. Green and blue, you get cyan, and blue and red, you get magenta. All right. But here you can see, if you put all those lights together, recombine them just like Newton did, you'll get white light. So this was revolutionary. This was a whole different way of thinking about color. But what is it? What is this white light? Well, it's a very small piece of what's called the electromagnetic spectrum. The electromagnetic spectrum is energy that permeates the universe, and it runs the full range from gamma rays to radio waves, depending on the type of frequency. If it's got long wavelengths and low frequency, it's a radio wave. If the wavelengths get smaller, the same material becomes microwaves. Then it becomes infrared radiation. And then at a certain wavelength and frequency, our eyes can detect it, and we call that color. But then if we go faster and shorter wavelengths from there, it becomes ultraviolet, and we can't see that anymore. And then we keep compressing them and speeding them up. We get X-rays, which can do damage to DNA and genes and cells, and then gamma rays, which will definitely do damage. So it's all this type of energy that permeates the universe. And depending on the frequency, the speed, and the wavelength, it manifests in different ways. And so color is just a small piece of this. Now, the traditional understanding of color, the one you'll get in an introductory textbook, whether it's physics or even in art, is that we see objects, A, because they're lit up, but that the color of the object comes from the light. So what would happen is if we look at this apple and we see it as red. The idea is that the apple itself, its molecular structure, its materiality, absorbs all the colors except for red. Red bounces off the object. It's reflected off the object, and as a result, we see that color as red. So if you think about this, it's a very, very strange and bizarre explanation, because it means that the apple is every color except red. The grass is every color but green. The sky is every color but blue, and so on and so forth, because all the colors become part of the object. The problem with this is that it's not strictly true. It's kind of on the right path, but if we understand the full picture, then there's a lot we can derive in terms of understanding how paint works. So what I want to do is explain how this is wrong and how we should be thinking of color. To do that, I have to introduce you to a scientific diagram called the spectral reflectance curve. This isn't one. This is just the beginning of me trying to explain one to you. So here's how it works. It begins to look fancy and very technical, but it's not. It's actually very simple. Let's take the full spectrum, okay, all the way from violet to red. And these numbers represent the nanometers, the size of the wavelength. So you can see red has the bigger wavelength and violet has the smaller wavelength. So this is the full range of colors that the eye can see, hypothetically. What the reflectance curve is a measurement of each of these colors that's coming off of an object, hence the term reflectance. Spectral meaning the color that's bounced off. So there are instruments known as spectrophotometers that film, shoot at, look at things, and they will give you a readout. They will tell you the light that's coming off the object, like that red apple we just saw, and it'll tell you how much purple, how much blue, how much cyan, how much green, how much yellow, how much orange, based on this scale. In this instance, the reflectance is 1 to 100, 100 being maximum, 0 being none at all. Okay, so if you had a reading that recorded everything at full strength, what color do you think you'd be looking at? And if you answered white, you'd be correct. And it also means you were listening to the lecture just a few minutes ago when we were talking about Newton. What if your recording looked like this? Only a tiny bit of each color. What color do you think you're looking at if this is what the instrument is picking up? And you'd be correct if you said black or dark gray, because it means there's barely any red, barely any yellow, barely any of these colors is being reflected from the object. And so when nothing comes off the object, our eye can't see anything, and it becomes just dark. All right. How about this one? This is halfway between the two. So what's halfway between white and black? This would be a gray. All right. So that's one way of thinking about this diagram, and it's very, very useful for everything we're going to be looking at from here on out. But notice the last word here, curve. And there's nothing curve-like about this structure, because it doesn't actually measure 7 things. It measures every single wavelength from 380 all the way to 720. So if you're measuring every single wavelength, what you actually get is something that looks like this. So there's tiny little stripes in here. So it's picking up every single wavelength of color. And when things are being reflected, it's never a perfectly straight line. Nature just doesn't work that way. So what you get is something that looks like this, depending on what you're looking at. Hence the term curve. So spectral, which means all the colors, reflected from an object, and what kind of curve do they make? And this is the crucial thing, because the shape of this curve tells us exactly which color we're looking at. And I'll explain that to you in just 1 second. Okay, so just want to make sure you're with me. This is a diagram for measuring color. So our eye will look at an object like the apple, but we can measure what the eye is receiving using a special tool called a spectrophotometer, who will measure each one of these wavelengths and measure how much. So clearly in this one, there's a lot more purple than there is green or yellow. Okay? So this is what daylight looks like. You take that thing and you point it up to the sky, not at the sun, just to the blue sky. This is what you get. You get a lot of blue. All right? This is where we're moving into ultraviolet. Our eye can't see that, so the purple drops off. And then infrared, our eye can't see that either, so the red drops off. And so the curve of daylight looks like this. Okay? Now this is important, all right, because I'm going to ask you this question. The yellow on this school bus, what would that look like if you were to look at it and measure it? So remember, the traditional explanation is this. We look at the school bus, the sun's shining on it, all the colors of light are present. They all hit the bus and they're all absorbed except for yellow, which hits our eye and we go yellow. All right. So if this is going to be our curve, I haven't drawn it yet, and this is the yellow we're looking at, what do you think our curve is going to look like? And for most people, they would say it looks like this because that's what's bouncing off the school bus, that yellow. Okay, you with me? But remember, when we looked at gray or white light, it had colors from readings. It was receiving energy and information from all the different wavelengths. So if yellow appears somewhat close to white, it's closer to white than blue or green or red in most cases, then if we only have this tiny little sliver, we're not going to see yellow. The color we're actually going to see is brown, because there's not enough energy here. The only way, because it only has one wavelength, the wavelength of yellow, in this case, maybe 580 nanometers. You can have a yellow beam of light, but it's not a single wavelength. The only time you get a single wavelength is with a laser beam. This is what the spectral reflectance curve of yellow for the school bus actually looks like. So you'll see it's reflecting all of the colors. Not a lot of purple and blue, a little bit of bluish green, some yellow green, a lot of yellow, a lot of orange, and a lot of red. And remember, when we put green and red together on that wall that we saw earlier, it makes yellow. In other words, there's an awful lot of light bouncing off that school bus. This is what's actually being reflected, not that single beam. So this picture needs to be corrected. Instead of just yellow being reflected, all of the wavelengths are being reflected, but mostly at this end of the spectrum, which is creating the effect of yellow. All right. So this curve tells us a lot about the composition of what's being reflected, and from there we can infer what the color is. So here are some paints. There's cadmium red, cadmium orange, yellow medium, cadmium yellow, light. And what you see at the bottom is the rainbow, but what you see up here is the particular curve. So you notice if you look at the red, it's got a lot of red and a little bit of yellow and green. And if we come down here to yellow, it's because it's almost close to white, right? If you look at it, it's very, very light and bright. It's got a lot of everything. And then it drops off in the purples. So you can see this yellow has blue. Has blue-green, has yellow, has orange, has red, and even has reddish purple at this end. So you can see the shape changes as we go darker. We get more of this black area, and what that is it means less light. It's cutting into the light, right? So this is just a little bit of light and then a lot of red, and progressively more and more and more. So these are the curves of these actual colors. And then we got to another set of colors. Notice here, the greens, the peak is in the green area, and in the blues, the peak is in the blue area. But notice also, even this blue has green, yellow, orange, red. Not a lot, but it does have it in there, and this is really important for understanding colors. All right. The other thing, we've been talking about color reflected off a surface. Now, an object can only reflect color if that color is in the light. And that's why the type of light and the quality of light is really important in our perception of color. All right, so this is daylight. Yeah. So daylight has all the colors in it, so that's pretty good. But this is an incandescent light bulb. The old-fashioned kind of light bulb that you screwed in that got really, really hot. This is the profile. This is the color profile of it. So what do you think it looks like? It's got green, it's got red, it's got yellow. It looks very yellowish. Yeah, if you take a walk at night and you look in people's houses or the rooms are lit up, if they have incandescent light bulbs, those rooms are kind of yellowy. And if they have LED, they're kind of closer to, pure white. They might even appear more blue or cool, especially also if the TV's on. So light itself contains colors, and different lights, their spectrum changes. So what would happen if you had a blue object and you shine this light on it? Well, this light doesn't have a lot of blue, so there's not a lot of blue to bounce back. This light has a lot of red, but there's very little red in a blue object. So what do you think you're going to get? Well, let's try that out. Let's just call this a rainbow with black and gray at the bottom. You shine white light on it, this is what you have, because white light has all the colors. What I'm going to do is I'm going to shine some colored lights on it. So this is a green light, this is a red light, and this is a blue light, and this is the original right here. Look what happens in the green area. The colors that have green in them light up. They have more light being reflected back. The colors that don't have a lot of green, like red, go dark, because there's not a lot of green to reflect. And if light doesn't reflect back to our eyes, it just looks dark. Same with the purple. Now if we go to the red light, look what happens. These look lighter, and now the green is getting darker. But notice the purple is lighting up. It's very different than this purple, and that's because there's red in the purple, and that red is being lit up. And in the blue, we can see this is one of the brightest colors right here. Well, for obvious reasons, it's blue. Now if I turn up the colors, a little bit more intense green, a little bit more intense red and blue, look what happens. The red turns black. Because this is a pure green light, there's nothing in here that's green to bounce back to the eye, so we see it as black. And this becomes very light. So if the room was just this one color, we'd think of this as white and this as black. Look what happens in the red. The opposite happens. Anything with green in it goes black, because why? There's no red in this color to reflect back. So when you shine only a red light on it with no green and no blue in it, there's nothing to reflect back. And same with the blues. All these go black, but the ones that have blue in it light up. All right, so this is crucial. This is why where you paint and the light you use when you're painting is absolutely important, because things might look one way in your studio or at home. Take it outside, put it in a gallery, put it in a friend's wall, and your painting can look totally different. And this can be quite dramatic. Here's another illustration of that. This is Mark Fairchild from the Munsell Color Lab in Rochester Institute of Technology, and he's standing there holding a photographer's color picker, and he's wearing the same t-shirt. Okay, so if the t-shirt's dark and he's in the green light, what does that mean? It means that what he's wearing has no green in it, which is why there's nothing to bounce back. This is light, it's lighter, which means what he's wearing can bounce back the light. So he's obviously wearing a red or orange t-shirt. Now if we look at what he's holding, the color picker, this is what it looks like. And I want you to look at this particular yellow, right? So come over here, and it's pretty bright. It's because it's yellow light. Here it goes a little darker, and then look what happens down here. It's dark. It's the second one down. Okay, so what does this mean when you're painting? Well, it means that if you're painting in a yellowish, orangish light, your yellows and reds are going to be nice and bright, and you might get them in balance with all the other colors. so it looks good. And then the minute you take it outside into a bluer, more daylight, now your yellows and reds look slightly duller and your blues and greens look brighter. Okay, so it throws it out of whack. So something we really want to pay attention to when painting is the type of light you're working with, which is why if you took a color class where you're mixing pieces of color, and you can't really go home and do it as homework, because if your lighting at home is different than the room, all your work is going to be completely different. But this is an important principle to think about in terms of color, especially when it comes to mixing, and we'll see why in a minute. All right, so coming back to the distribution curve of daylight, and if we're mixing colors in daylight, we're getting all of the colors available, so our painting is going to have a nice representation. If we're working with bulbs that don't have everything, we get something like this. So you always want to make sure you're working with a daylight bulb. You can buy them, LED daylight bulbs, or any kind of bulb that says daylight. It gives you the full spectrum of light. All right, so that's a lot of the physics of color. But the problem is it's not just the physics. And this, again, this is what you find in many textbooks or websites, that light is a property of the wavelength. That's not strictly true. Wavelength is necessary, it has to be there, but color is much, much more than that. And what I mean by that is that context, the things next to it, play a crucial role in how we see colors. So for example, these two little objects here, for all intents and purposes, are gray. They're the same. Maybe one's got more lighter gray than the other, but that's not the point. Point is, I'm going to color the space around them, and what you're looking at is going to change color. Okay, so I'll go back. So it's the same object. You see that? And we come here. So now this has gone yellow, and this has gone kind of bluish. All right, so there is no yellow here. This is a complete illusion. And there is no blue here. What's happening is your brain is seeing the whole scene, and it's making a calculation. It's saying, well, if I'm looking through a blue filter and something appears, if something's reaching my eye and it's reading as gray, which is what it is, well, the only thing that can hit my eye as gray if it comes through a blue filter is a yellow object. So therefore it must be yellow, so we see yellow. And likewise over here. So it takes that neutral color, and because it's neutral and everything else has color on it, it takes on the opposite qualities of this particular lens that we're looking through. Okay, so this is not an unusual thing. The environment will affect how we see color in a great many ways. Here's another example. These two are exactly the same color. They're this brown. What's happened is all these colors on top have now shifted into shadow over here. So they've all gone darker. But this one hasn't gone darker. It stayed the same. Yeah. So what our brain is saying is that if this is what it looks like in the shadow, everything else is so dark. So in the light, this must be almost fluorescent. It has to be bright. And so we make the calculation that this is not this. This is more of a bright orange color. All right. So this is what we're actually seeing, but this is what we think we see. All right. So that's an important thing to know about color. It's not the wavelength. It's the context. It's the environment. It's everything you have working around it. We saw something like this earlier with value, the light and dark. Same with, light and dark. But it works with color also. I take the color away, and they're the exact same. Put the colors in. One's yellow. One's kind of a blue-gray. All right. Same thing here. These strawberries are not red. There's no red in this picture. In fact, if I take a little piece of one of the strawberries, copy it and paste it, this is what I get. It's gray. Again, it's the exact same thing we just saw earlier. Our eye is picking up gray, but our brain says we're seeing it through a cyan blue-green filter. So the only way something can be gray coming through a blue filter, meaning it doesn't have any blue in it, is it must be red. So our brain is filling in the colors that aren't really there. And you can see it's the same gray if I slide it over. Okay, so to wrap it up, when we're looking at color, there's lots of components. Three main things. There's the light, the quality of the light, the type of light. There's the object, how much it reflects. And then there's the viewer. What does the viewer see when they see the object? And we haven't talked much about the physiology of the eye and color blindness. Different viewers can see the same thing slightly different anyway. But here I'm saying, looking at something, we often don't see things in isolation. We see them in context. If you're looking at a blue shirt, you never see it against a pure white floating background. It's always in a wardrobe next to other colors or on somebody. And so these three components are really what makes up the science behind color. So I'll leave you with this question. If there's no light and no observer, is there color? So if you took your blue shirt and you put it in the closet and you close the door, is it still a blue shirt? This is not a philosophical question where you can debate it. It's actually a factual question. The answer is no, it's not a blue shirt, because blue is a property of light and observation. Take away both of those and you don't have any color. Okay, until part 2.